Hello, and welcome back to Discovering Code. And today we are solving Yarik and Array problem. Guys, I have completed till like the 1000 series is done, 900 is done, 800 is done, and now we are working through 1100. And yeah, um, also there's a Code Forces Div 3 contest that's going to be happening on 5th September. Today is 27th August 2026, so we are going to be uh, aiming for that contest and see where we end up after solving like these many, hoping to solve at least ABC of that contest, but we'll see how it goes. I will probably live stream that as well, but yeah, let's get into this problem. Yarik and Array. Now, before looking into the details of the problem, let's do one thing and let's get the time complexity and the space complexity sorted. And that should give us a hint of what, it's written right over here what algos are going to be used, but we still want to know the time complexity because it will help us narrow down exactly what algo we might be using. So time limit per test is 1 second. 1 second translates to roughly 10 to the power 8 operations. And what is our input size? So each element can range from minus 10 to the power 3 to 10 to the power 3, and the total length of the array is 2 into 10 to the power 5. So let's say if each element is 10 to the power 3, it doesn't really matter what is the, okay, it does if we are, okay, what do we need to do here? We need to check the parity, right? That means we need to do modulus operation. Modulus is O of 1. So it doesn't really matter what is the size of the element, since we just need to check the parity and then choose the sub array. Okay, to choose the sub array, we need something like a sliding window or 2 pointers, right? To iterate through the whole array. And so so what I was saying is it's O of n operations, O of n. And O of n here is 205, which is less than 10 to the power 8. So O of n is okay. What about n square? N square is definitely not okay, because if the length of the array is 10 to the power 5, 20 to the power 5, and we double it, then obviously it's more than what we are allowed to have. So n log n, what is the log of 2 into 10 to the power 5? Log of 10 2 into 10 to the power 5. So 5. It's, yeah, I think we can do that as well. 5 into um, 2 into 10 to the power, no, into 10 to the power. Okay, this is also acceptable. So yeah, so we can do O of n log n, but that's it, nothing more than that, and anything below it also works. Okay, now let's read the problem. A subarray is a continuous part of the array. We know this. Close these out. Oh wait, how do I control D? No. Shift D. Okay, Control Shift D. This was a different problem. Um, okay. Okay. So we are given subarray. Oh, it's black. Subarray. Sorry again. Let me delete that. Yeah. So Yarik recently found an array A of n elements and became very interested in finding the maximum sum of non-empty subarrays. However, Yarik doesn't like continuous integers with the same parity. So the subarray he chooses must have alternating parities for adjacent elements. So two things, what does adjacent means and what does parity mean? So parity is basically nothing. It should be either, oh my god. Okay, how do I, you know what? Yeah, this is better. Okay, let me make it black again. Pure black or yeah, I like this black. Okay, let's stroke that is fine and we need it white. Good. So what does parity mean here actually? Mm, so let's say a number is 2 and if we do it we get a 0, right? Because there is no remainder. So this means that this is even. Uh, and if we do like 3, 2, we get 1, right? This means that it's odd. And a parity is nothing, it's just even and odd. I mean, the definition of parity is definitely more than even and odd, but in this case, it's just parity means the state of condition of being equal in status, value, or amount. So mathematics, since we're solving a code forces problem, we obviously look at the parity in mathematics terms, so even or not. But in financial, currency parity, two different currencies trade at an exact one-to-one exchange rate. So yeah. Mm, okay. So now that is out of the way. If we can look at the example, it's 1, 2, 3, 1, 2, 4. So this is a good example. This is a good answer, is acceptable. But this is not because the adjacent elements, meaning the one beside the current element. So let's say our current element is 2. What is the one beside it? It's like both ways actually. But since we'll iterate linearly, we'll only check to the right. Uh, so to the right, what do we see? It's 3. So is 3 the same parity? Is it odd or even? If it's even, it's not acceptable. As in this case, it's not acceptable. In this case, it is acceptable. Now our problem is to find the max sum of such a subarray. So we need to find a subarray and then we need to maximize. So we need to find a subarray which has the maximum sum of such that fits our conditions of adjacent elements having alternate parities. So how do we do this? It says DP over there, but I don't know. DP would be to go into all of the possible states. But since we are in a time constraint, which is often n log n, um, I don't think DP would. I mean, greedy also comes under DP, maybe. I don't know. Okay, let me search. Mm, Does a greedy solution also qualifies as a dynamic programming solution? Okay. It comes conceptually be viewed as an extreme or simplified case of a dynamic programming. Choice processes. A greedy algorithm makes one choice at a time at each step and never reconsiders or looks back. Yeah, that's the key thing. Looking back, dynamic evaluates multiple overlapping subproblems and uses a table or memorization to decide what's the best path. Exactly. So, okay, let's say if a problem. Okay, wait, we have from 11 years ago for Ilve iOS. I'm so sorry. It so happens that apart from being an active member on code for the, I see a question where the most overruns is not entirely covered. This is take a look at this question. Okay, what is this question? Okay, I'm going through a rabbit hole right now, but okay, this is fun. How is dynamic programming different from greedy algorithms? In the book, I'm using introduction to is said to be focused on the principle of optimality. Big word. An optimal solution to any instance of an optimization problem is composed of optimal solution of its subinstances, whereas the greedy technique focuses on expanding partially constructed solutions until you arrive at a solution for a complete problem. It is then said it must be the best local choice among all feasible choices available on that step. Mhm. Dynamic programming is applicable to the problem by exhibiting the following properties: overlapping subproblems and optimal substructure. Optimal substructure means that you can greedily solve subproblems and combine solutions to solve the larger problem. The differences between dynamic programming and greedy algorithm is that dynamic programming there are, oh my god, there are overlapping subproblems and those subproblems are solved using memorization. Memorization is a technique whereby solutions to subproblems are used to solve other subproblems more quickly. This answer has gotten some attention, so I'll give some examples. Consider the problem: making change with dollars, nickels, and pennies. This is a greedy problem, so it exhibits optimal substructure because you can solve for the number of dollars, then solve for the number of nickels, then solve for the number of pennies. You can then combine the solution to the subproblems efficiently. It does not really exhibit the overlapping subproblems, and solving each subproblem doesn't help much with the others, maybe a little bit. Because of the problem Fibonacci numbers, yeah. It exhibits optimal substructure because you can solve F10 from F9 and F8 efficiently by addition. These subproblems overlap because they both share F7. If you memorize the result of F7 when you're solving F8, you can solve F9 more quickly. That is true. In response to the comment about dynamic having to do with reconsidering decisions, this is obviously not true for any linear dynamic programming algorithm. The maximums have a problem or the Fibonacci problems above. Essentially, imagine a problem having optimal substructure as a direct acyclic graph whose nodes represent subproblems, wherein the whole problem is represented by a node whose in degree is 0. Okay, in degree 0 meaning no incoming nodes. We have a node, no incoming nodes. So only outgoing nodes. So this has an in degree of, okay, wait, I shouldn't draw that. So this has an in degree of uh, degree of 0. This has 2. So yeah, that's what it means. Um, so imagine a problem having okay, acyclic graph whose and acyclic meaning so all the nodes you can reach one node to the other node somehow somewhere. So if you can't, then it's an acyclic. Say I have these many nodes, right? 4 nodes. If I have this, and um to reach to this, can I reach? Yeah, I can. I need to reach, okay, this. So this is a and from for each single node, can you reach all the nodes directly or indirectly? So if I want to reach here, I can go here, then go here. I can reach. If I want to go here, I can go here, here, I can reach. If I want to go here, from here, I can go here. If I want to go here to here, I can go here, there. See, so it's cyclic. even though it doesn't look cyclic, it is cyclic. I chose a bit complicated one because just to make my concept a bit more clear. But okay. So, having optimal substructure as directed acyclic graph whose nodes represent subproblems, when the whole problem is represented by a node whose integer is 0, whose directed edges represent dependencies between subproblems, then a degree problem is a tree. All nodes except the root having unit in degree. A dynamic problem has some nodes with an degree greater than 1. This illustrates the overlapping subproblem. Okay, I have read the acceptance answer. Let's read the discussion is pretty much on what is greedy and DP, and isn't one of them a subset of the other. And the difference between dynamic and greedy algorithms is that the dynamic programming has subproblems overlap. I did. I think so. Is that answer right? Yep. Yep. We read through all of that. Okay. In fact, the whole answer is quite interesting. I tried to start a discussion with the poster explaining what is wrong, but I kept getting more and more interesting statements. Here is an example in the comment section. No, Dijkstra's without the heap would be a greedy algorithm. Hmm? Really? The heap introduces a dependency whereby when a decision is made about the solution to a subproblem, the shortest path to a vertex is used to facilitate the decisions to the other subproblems. This is why Dijkstra's is not simply a greedy algorithm. Or else, why would you make the decision independently? This agrees with the top core answers, Neil G. If you also read through the chat, you will notice that the same user claims that computing the nth Fibonacci number using memoization in DP, which is correct, but without memoization, it would be greedy, which is not. I mean, yeah, true. Uh, Even without using memoization, it is going through each of the following like subproblems, and it needs so it grows massively. In greedy, we only look at, let's say this is our current state, and we look at this state and we see, okay, which one is the uh, best optimal one. In recursion, we look at the whole tree, so it goes like this, like it increases like that, right? And like that and like that, and then it keeps going, right? So greedy just stops here, but recursion, we look here, we look here, we look here, we look here, we look here. So there are levels in recursion, whereas greedy is just looking at the current status and just finding out what's the best possible move we could make to maximize or minimize whatever the question requires for that current output. So it is the first time I see an accepted answer that is so off target and where the poster ignores any reasoning. Truth is that this case annoys me quite a lot. I see something that is totally incorrect, and yet it seems to be accepted by the community. More people would read this answer and most will believe it is correct. Thus, I'm turning to Code Forces community for some support. Apparently, my opinion is not authoritative enough and the links I provide are not enough. I would like to hear to, I would also like to hear what you think on the whole discussion. It makes no sense to argue whether Dijkstra algorithm is or isn't greedy. There is no formal definition of what it is and what isn't a greedy algorithm. The word greedy, in an informal way of describing an observation during problem-solving algorithm design, we use being greedy as a shorthand for making the more locally optimal choices. That is true. Hence, when we say the problem can be solved greedily, we mean the sequence of locally optimal choices will actually bring you to the global optimal solution. As for Dijkstra, is there a greedy aspect to the algorithm? Certainly, yes. I mean, obviously, that's what started this whole rabbit hole, right? Is that if a DP problem can a greedy problem be categorized as a somewhat DP problem? And I mean, is the greedy aspect? Obviously, there will be in any dynamic problem. There will be when you look at the most minute, most smallest structure. So let's say here, right, when we're creating these, so while creating a node or while comparing two nodes at the same level, there will be involved some comparisons or something like that that would seem greedy because it is greedy, but dynamic programming is more than just the local thing. So we look at the whole thing and we come to the conclusion of what would will be the most optimal answer for our uh, problem that involves multiple layers and multiple steps and multiple levels in the recursion tree. Uh, Certainly, yes. You always select the current best unprocessed vertex. That is exactly what my point is. To be processed next. Should the algorithm be classified as a greedy algorithm? No, because such classification would mean misleading. Would be misleading. This is because the greedy choices are not everything the algorithm does. Exactly. Processing a new vertex does actually change the state of the algorithm and influence the future choices it will be making. The algorithm has to store and reuse information in a clever way in addition to the greedy choices it makes. Similarly, there is a dynamic programming aspect to Dijkstra's algorithm, but I believe it is misleading to label it as a pure dynamic programming algorithm. It's not just a single recursive relation where each subproblem only references other, strictly smaller subproblems. Most of the arguments about such topic arise because people care too much about names and categorizations and they care too little about the actual ideas. Oh my god, this is such a good answer. You should enter into the system before you vote. Enter into the system? Question mark. Am I not logged in? Oh, I might not be logged in. Am I not logged in? Oh yeah, I'm not logged in. Ah, crazy. Please remember me for a month. Yeah, just I'm bad. I'm bad, guys. Okay, let me afford. I agree with what you say. The reason I'm starting this is because I believe they accept proposals as well. What is created. Maybe there are better places to spend your energy. Don't worry too much about future learners. Nobody is forcing them to accept any answer at face value. They also get to think about them and decide whether they agree. There is a long way from asking the question, what is the difference between greedy and deep? To understanding the the question is meaningless. And maybe it's actually good to read many different disagreeing opinions at some point during that journey. From Slovakia, he's a master. He has only solved 41 problems. Uh, but 211 rating. Goddamn. The GOAT. His starting rank was expert. Was it? I don't know. 2010. Seems like it. Okay. Let's get back to the question, guys. It's already 23 minutes into the yapping session. So, how do we solve this? I'm thinking we just do two pointers uh, and we keep increasing the subarray. And once we find a parity break, we calculate the max and then we reset the window, then we go again. I mean, that is the most straightforward and simple solution that I can think of for this problem. Um, so yeah. Okay, let's dry run that then. One, two, three, five. Okay, so parity break. We get one. We point both of them at the same element. Then this is the left one, this is the right one. We increase the right. We check the parity. No parity break. We increase the line. Okay, wait. So we need We don't increase left, we only increase right, and we check r with r plus 1. And if that's good, then we go ahead, then we check r with r plus 1 again. If that's good, we move ahead. If we check again, r plus 1, if it's good, we move again, r plus 1, if it's good, we move ahead. If we reach the end of the array, we just calculate the whole thing and return. So here the max sum is, yeah, 9, 12, 14, 15. And that seems to me like a good solution, but let's see. Okay, let's take the negative one as well. Okay, we have negatives here. Okay, that makes it interesting. To check parity, we'll have to strip the negative sign off. But also to maximize it, okay, to maximize it, we need to, I mean, yeah, -1, 4, -1, 0, 5. That seems like the best optimal solution. But is it not? We're getting 8, right? Yeah. Oh, okay. Best optimal is 4 -1, 0, 5, which gives us 8, which is the max. Okay. How do we deal with negatives? Do I just code it based on the first? No, 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 I shouldn't. I shouldn't, because minus. I need to take care of the negative sign as well, and I need to think, how do I handle that case? Mm. Okay, if we look at the fourth, if we look at the fourth one, the output is here. If we do it, it's 1. Here, if we do, it's 1, but the answer is 4. Okay, okay. Each subarray can be the one single element in itself. So that makes sense. Mm. So one thing is the max element present can be an answer. The alternating parity. So in this one, the answer is 9 plus 8, right? Yeah. Alternating parity. Parity. Sorry if you can't read that. I can't either. But I'm bad with the mouse. Then uh, negatives. Handling negatives. Handling negatives. Maybe I should have become a doctor with that handwriting. uh, Here the answer is 101. Yeah. Okay. Mm, 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 mm. Okay, so we initialize, to handle this, we initialize our answer with the max element present. Then uh, to handle negatives, and parity, we do nothing. We just do the algorithm of increasing, checking, increasing, checking, increasing, checking, right? But will it cover all of the possible sub-arrays is what I'm thinking. It won't, because it will. Uh, wait, it will. Okay, let me go through one actually. Okay, -2. Sorry, -1, 2, 4, -3. So left is initialized here, right is initialized here. Our max is 4. And then we check parity. Parity good. We check parity. Parity same. So we check max. Max will be 1. So 1 comma 4. Max will stay 4. Then we increase L, and we reset R to L as well. We increase L and we reset R to L as well. And then we check parity again, is the same. Then we increase L again. But after checking the current element and the max element, uh, uh, then we increase it again, R here. Then we have 3, parity different, so we bring R here, end of the array. Then we check the current max, the current sum and the max. It's 1 comma 4. We get 4. We return 4. I think it will work. I think it should work. Yeah, I think it will work. I mean, I think it should. So yeah, let's go ahead and try to code it out. So we have also sending a lot of strength to Nepal. Uh, I just saw what happened there. Very extremely heartbreaking. Natural disaster. Um, I mean, I have no idea how it happened. Everything was looking fine. It was bright, sunny day, and then after out of nowhere, um, yeah, India has sent help to Nepal, but yeah, I'm sending a lot of love and strength, and uh, I hope that everyone stays safe over there. Yeah. Okay. Int array is new int n. Okay. Take input. Mm, mm, mm. Okay. I need to how to find the max element in array in Java in one shot. I think there is a direct. Okay. So it's arrays dot stream the whole array, dot max, get the max, get as int. Oh, what does it return if I don't add int? What does it return as? It returns it as optional int. What does optional int mean? Okay, let me search. What does optional int mean here? Returns as optional int describing the maximum element of the stream, or an empty optional if the stream is empty. Oh, okay. But we know it will be returned as an int, right? So what does get as int does? If a value is present, return the value, otherwise throws no such element exception. Oh, okay. Great. So that is done. We have the max element. Now we begin our left and right. search while right is less than n. So we check r with r+1. Check parity. If ARR of right modulo 2 is equals to 0, and then ARR of right plus 1 is equals to 1. So like different parity. I don't know if this is the best way. Oh wait, I missed a condition. Modulo 2. I don't like this at all. Oh, nest. 3 levels of nest is bad. Bad code. But let's see. We're learning. If your right model 2 is equals to 0, right plus 1 model 2 is equals to 1. I mean, I should write not equals to 0, not exactly 1. That is too restrictive. Yeah, this is better. If that's the case, then right plus plus, increase the window. If that's not the case, if we have found similar thing, then we need to add all the elements from there to here. So I think it would be better to have a prefix sum array, right? So that we don't need to iterate it over and over again. So let me create a prefix sum array. Prefix sum that handles it, right? So the previous one and the current one, yeah, that handles it. Okay, so here we can just say max is equals to math.max of prefix sum of current right element, right? Or right minus 1. Will it be right minus 1 or will it be right plus 1? I'm checking right. Then I'm checking for right. Yeah, it will be right. Right comma max left plus that left, then we print. I don't know, let's see. I pasted it twice. Is this correct? I think so. What happened? Oh, it's still running. Oh, wait, it's my loop. Error knows. What if it's the last element? Are we... Oh, I need to do it once more, right? I think I need to do it once more. Uh, I need to do this check once more. No, that's not the issue. I mean, I need to do it once more, I know that, but something is not right. It's going into... If they are never... Say they are never in parity. So they're always in parity. What then? So does my code handle that? It only does right plus plus when they are in opposite parity. And if they're not, then it does left plus plus and then brings right to that current left. And check parity again. No parity, left plus plus again. And but why am I doing prefix sum here? Oh my god. I need to check for the gap and not, I mean, but still some answer should come. A wrong answer is better than no answer. Yeah. Did I? Oh my god. Oh my god. A hint would have helped. A hint would have helped. Okay. Alright. It's time to debug. Let me ask Gemini over here. Want you to help me debug my code for this problem. I wrote a simple solution which I think works on paper, but I have not done a good job of translating it into the code. I don't want you to give me the right answer. I want you to teach me how to get to the right answer. Here is my code. Okay. Let's break down where logic diverges from the problem requirements and how your current implementation behaves. All right, here we go. Oh, yeah. I need to check its absolute value, right? Oh, yeah. Kadane's algorithm. Is this Kadane's algorithm? Oh my god. Oh yeah. Okay, let me read this. This problem asks for maximum subarray with alternating pair, which is a variation of the classic Kadane's algorithm. Our solver is using prefix sums, two pointers. The issue in Java, negative even model 2 yields 0, but negative odd yields -1, not 1. White breaks. Checking fails when odd numbers are negative, causing the alternate check to incorrectly return false. Okay. How to fix? Check relative parity using, I mean, yeah, absolute is what I thought. Or maybe yes. Yeah, I'll do that. I'll need to add ABS here. I actually discussed it as well in my writing of it, but I forgot while translating it to code, which is bad. One mustn't forget. What mustn't? What one must something something to quote Shakespeare or Sun Tzu. Okay. Subarray sum from prefix sums. The sum of subarray from left to right is sum left to right, prefix right minus. Yeah, exactly. That's what I thought. Uh, that's what I thought. I realized after a while. Not that -1. I need to do this in an if statement. If left is not 0. Yeah, the main problem is the pointer reset. Uh, you're comparing max against prefix sum, right? This only measures the subarray starting at the index 0. If left is greater than 0, prefix sum includes the elements before left that shouldn't be in your sum. Exactly my point. I was only worried. So it was like what I was doing. I said that I'm checking this, right? I said I'm checking this, but actually I'm checking this. And I should include should not include this. So how do we not do that? We actually subtract whatever is here from the total, and we get this. So yeah. But now the main point is the pointer reset and the complexity. So resetting it back to left makes it O of n square because I am doing this. I am doing this. Oh wait. So like we have these many elements. I go here, I go here, I go here, I go here, I come back here. Sorry, and then I go here. I'm not here, but let's say here. and then I go here, 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 come back here, here, here. So that's almost n square. That simulates n square, not n. So y parity breaks, your reset left plus plus, and then set right equals left. Y breaks, resetting right back to left turns your loop into a form of n square, which will cost TLE. Exactly. When parity breaks at index right, any valid alternating subarray starting at or before left cannot extend past right. You can simply restart your current valid segment directly at right plus one. Okay. Yeah, true. So we had left. So what it's saying is that we had left here, right? And then we had right here. And say our parity breaks here. So anything past here will be smaller than the current window that we have. And so it will not actually help us maximize the sum. So we can directly restart our window at right plus one and move L to R, right? So let me do that. Mm, we can make it, we can make left equals right plus one and right equals left. Yeah. Oh, God, this is such bad code. God. Okay, you know what? Can you simplify it to current sum and max sum? Has different priority. Yeah, let's do that actually. Let me just let me remove everything from here to here. Let me make a current sum and a max sum. Max sum will be arrays dot stream arr dot max dot get us in whatever is max and return max sum, and for n I equals 0, I less than n, I plus plus. Should I start at 1 because we'll be looking back anyways. So yeah, let's do that. And then max alternating sum ending at the current element. I think it told me a easier version. Arrow 5. Okay, that seems to be much better. So if they have different parity, it will obviously be not equal to 1. Sorry, not equal to 0 if they have the same parity. So this is XOR operation. Arrow of I minus 1. Let's do that. This one, modulo 2. So if the previous and the current are different. It will not be 0. That means they have alternating parity, and we will do current sum. Is it greater than 0? If yes, then current sum plus equals to AR of I, and if no, then else current sum is equals to 0. Sorry, current AR of if it has the same parity, I mean, I'm just translating, but if it has the same parity, then we will break the chain and start fresh. And then we update max sum is equals to math dot max of current and max. Wow, look at that code and look at the code I wrote. Oh my god. There we go. Exactly the answers we required. But okay, there's a parity check and negative subarrays. So as I pointed out in my initial handling negatives, I could not do that. How do we handle negatives? So it was even with a valid alternating segment, if your running sum drops below 0, I was not having a running sum. I prefixed it. So that was a gap there as well. So even with a valid alternating segment, if your running sum drops below 0, keeping that prefix only decreases the sum of any future subarray extending from it. That means that, let's say, if we have like 2 or 3 negative numbers and our running sum drops below 0, any additions to it that will extend from it will not help us reach the max that we require. So if your segment runs becomes negative, just reset your running sum to 0. That's it. So that makes a lot of sense. Okay, I think this will work. It's almost an hour, but yeah, I was a long way off. I forgot Kadane's algorithm like completely, and I mean, this is classic Kadane's, but yeah, it's kind of deflating, but yeah, it's okay. Where is it? There it is. Okay, let me remove these and let me make it main. So I did enjoy, but I wanted to solve it on my own, but I couldn't. So yeah, we keep going though. We keep going, gang. We keep going. And with that, I'd like to end it directly on the 1 hour mark. Take care, be safe, and I will see you in the next one. Bye. Bye.